From CHIJ School, this is Eileen, she's Sing and Anna. The title of our project is Development of Bio-composites using spent coffee beans for packaging applications. This project aims to promote sustainable development by developing bio-composite materials from polylactic acid, PLA, virgin polypropylene, VPP, and recycled polypropylene, RPP, with spent coffee beans as materials. Mechanical properties and carbon footprint of the developed materials will then be analyzed and compared. The eco-efficiency of which will be calculated from the mechanical properties and carbon footprint.
Basically, sustainable development addresses the needs of the present without compromising the needs of future generations. And therefore, we have decided to develop a bio-composite, which is a bioplastic, to reduce the use of fossil fuels to promote sustainable development.
So one may ask, why do we choose to use coffee beans? Coffee beans are actually chosen as the natural filler for the bio-composites, as it is a natural source that can be found in abundance locally to promote the use of renewable material and food waste as an environmentally friendly alternative to conventional plastics.
Basically, there are two main activities covered in this study. Firstly, bio-composites are developed through compounding extrusion of PLA, VPP, and RPP, followed by injection molding to form the prototypes for mechanical plastic. Secondly, carbon footprint is quantified through data collection and through the production of bio-composites.
Now, moving on to talk about material development. In this study, bio-composite materials were produced by compounding spent coffee beans with a polymer. Firstly, there is the drying of the natural filler. The coffee beans collected were heated in an oven to a temperature of 90 degrees Celsius for 2 hours to remove any moisture present before compounding. Secondly, there is the compounding and extrusion of the bio-composite. The polymer and the coffee filler were compounded at 190 degrees Celsius in the macro extruder according to the desired compositions, where the bio-composite was extruded twice to ensure more homogeneous mixing of the polymer matrix and coffee filler. The extruded strands of bio-composite were then pelletized for injection molding process. Thirdly, there was the injection molding process. The mini injection molding machine was used to produce tensile bars and impact bars for testing and miniature fork samples for display purposes. During molding, the pellets were melted in the heated cylinder and then injected into the heated mold to form the desired shape. Under mechanical testing, the tensile strength, tensile modulus, and impact strength of the bio-composite materials were tested to ensure that the materials are strong and flexible enough for commercial usage. The results obtained were then compared to that of the neat polymers to analyze the practicality of replacing the neat polymer materials with the bio-composite. Two main data types for carbon footprint quantification are activity data, for example, energy and material consumption, and the emissions factor, for example, the conversion of activity data into carbon footprint. Based on the results obtained, the bio-composite made from virgin polypropylene has a higher overall carbon footprint, as its embedded emission due to production process is the highest. On the other hand, as recycled polypropylene was collected as waste, the carbon footprint attached was minimal. Although results showed that the recycled polypropylene had the least amount of carbon footprint than polylactic acid and virgin polypropylene, the difference with the addition of the filler material was much less with recycled polypropylene than polylactic acid and virgin polypropylene. Results show that with an increase in the composition of natural fiber, the carbon footprint is reduced. However, with a compromise in the tensile and impact strength of the materials, although polylactic acid has better mechanical properties than recycled polypropylene, its carbon footprint is higher, resulting in the eco-efficiency of the bio-composite compounded with 60% by polylactic acid and 40% by spent coffee beans being slightly lower than the bio-composite made from 60% of recycled polypropylene and 40% of spent coffee beans. Nevertheless, as the life cycle inventory of the polymers was only considered from cradle to gate, the results might differ if the scope were to extend and include usage and disposal. Therefore, polylactic acid, being degradable, may be able to induce lower impacts at its end of life compared to that of the recycled polypropylene.